Welcome to our 4th week tutorial where we will solve the assignment problems. So, let us start the problem number 1. I read out: a satellite link has same carrier to noise ratio in uplink as well as in downlink. Both uplink and downlink have same carrier to noise ratio. The overall carrier to noise ratio of the link will be always less than that of individual, either uplink or downlink, always greater than the individual, equal to the individual ones, or unpredictable. So, let us see, this is a simple thing. The concept wise, the answer, if you recollect, C by n or total or C by n, if you say, inverse of that is a parallel combination of C by n naught up inverse plus C by n naught down inverse. Now, these C by n's are all in ratio, okay, and since it is n naught, Hertz is the unit, okay, inverse of Hertz. For C by n naught up is equal to C by n naught down, that is what is the condition given. So, you replace one of them, either up, in case of down you put C by n naught up. So, it will become half of C by n up, or the other way, half of C by n naught down. So, C by n naught total will be half of any one of the individual. So, it will be lower. So, appropriate option will be A. Let us go to the second problem. If 500 watt of RF power is fed to an earth station antenna and that power is such that it saturates the transponder having saturation flux density, SFD is saturation flux density of minus 86 dBW per square meter at a distance of 40,000 kilometer. So, the power amplifier output from the ground station is such that at this distance the flux density which is reaching the satellite is minus 86 dBW per square meter, and the value is such that it saturates the output amplifier, that is EIRP gets saturated. So, it is called saturation flux density. So, from this you find out earth station transmit antenna gain. Let us see how it can be done. Given saturation flux density of the transponder is this minus 86 dBW per square meter. The input flux density at the satellite IFD is the transmitted power by 4 pi r square flux density. So, if you put the numbers, you get minus 136 dBW per meter square. I converted into dB, from the ratio I converted into dB. This is input flux density, and antenna gain required to saturate the transponder is saturation flux density minus input flux density, that is subtract these two, you will get 50 dB, that is the antenna gain of the that is the antenna gain 50 dB. So, appropriate option is B. Let us go to the third problem. Those two are much simpler. Let us see. A geostationary satellite has an elevation angle of 35 degree with respect to a particular earth station which is at mean sea level, and of course, with the ground, that is the elevation angle. The earth station is operating at 4 gigahertz downlink frequency. The specific attenuation due to stratiform rainfall, the downlink is 1.4 dB per kilometer. Determine the signal attenuation in the downlink assuming the rain height of 3 kilometer. The informations which are given here is the ground station to satellite elevation angle is 35 degree. Second is it is a stratiform rain, it is uniform rain, and there is a rain height of 3 kilometer, and specific attenuation is given as 1.4 dB per kilometer. So, we have been asked to find out what should be the attenuation, total attenuation when the signal passing through the rain. There are various options given. So, let us try to draw a picture. So, this is the earth station which is at mean sea level. So, this height we ignore compared to the satellite height as well as the height of the rain where it is rain forming. So, it is called rain height, which is 3 kilometer already given, and this elevation angle is 35 degree. So, if we know the, and it is a stratiform rain fully covering, and there is no, at one place there is no convective rain, it is continuous homogeneous rain, let us say. So, this signal which is passing through the rain, and beyond the rain it will be passing through the other that is almost vacuum above atmosphere, let us say. So, attenuation will happen here, and in that per kilometer how much attenuation that will happen, that is specific attenuation which is given. So, if we can find out what is this distance which is passing through the, when signal is passing through the rain, then multiplied by specific attenuation you get the total attenuation, and this is angle is given, the perpendicular is given, hypotenuse, this is right angle triangle, let us assume. So, this is hypotenuse L can be found out, this L is d by sin 35, d is in this case height. So, 3 kilometer by sin 35 degree, which is 5.23 kilometer. So, this distance L is 5.23 kilometer, and specific attenuation is already given, which is 1.4 dB per kilometer. Multiply these two, you will get 7.32 dB. So, the nearest option is B. The question 4 says a standard earth station with G by T of 30 dB per Kelvin receives a signal that measures C by N naught of a satellite beacon, and that measured value is 90 dB Hertz. It is a standard earth station whose G by T is known, whereas the C by N naught of the same beacon measured at the same location co-located by another terminal which is very small aperture terminal, and there the C by N naught value is 70 dB Hertz. Determine the G by T of the VSAT station receiver. There are 4 options given, 10, 11, 12, 13 different options given. Let us see. So, try to recollect, C by N naught of the downlink of the standard earth station is EIRP of the beacon plus G by T of the standard earth station minus losses in the downlink minus K, and at the same location C by N naught of VSAT, downlink is measured at VSAT, which will be same EIRP beacon, same thing is measured, only G by T of the VSAT, downlink path loss because same frequency it is same, Quay's Boltzmann's constant is same. So, if you want to find out G by T of the VSAT, you change the site, it becomes G by T of VSAT. Actually, what you can do, you can subtract these two expressions and you get G by T of VSAT is G by T of the standard earth station minus difference of C by N naught measured by the standard earth station and the VSAT. So, that is delta C by N, let us call, and the values are G by T of the standard earth station given 30 dB per K, and C by N naught value measured at standard earth station and VSAT are 90 and 70. So, if you put into this expression, you get G by T of the VSAT is 10 dB per K. This is the method of measurement of G by T by comparison method. So, correct option is A. This is more elaborate. In a point to point satellite communication system, the carrier signal at the satellite as received over the uplink is 40 dB greater than the strength of the interference signal from an interfering earth station. So, the uplink carrier to interference is the difference is 40 dB. Also, the strength of the signal power received at the desired earth station over the downlink is 35 dB more than the strength of the interference signal due to interfering satellite. So, in the downlink there is a carrier to interference is 35 dB. So, uplink C by I is given, downlink C by I is given, determine the total carrier to interference ratio of the satellite link, very easy. So, there are various options given 30, 34, 40, 44. Let us see. It is same as C by N naught of uplink and downlink, same thing in carrier to interference alone. So, carrier to interference total will be in the similar expression, carrier to interference total inverse is equal to carrier to interference uplink inverse plus carrier to interference downlink inverse. These are all in ratios. So, you calculate with ratio, and so you get total C by N naught inverse is 2402.5. When you convert, it becomes 33.8 dB. The correct choice is B. Assume the noise power associated with the GPS signal over 2 megahertz bandwidth is minus 141 dBW. If there are 10 satellites visible to the receiver, and for simplicity assuming power from each satellite at the receiver is minus 160 dBW, what is the SNR? That is the including the actually SNIR, it should be signal to noise ratio and the interference what is coming at the receiver output. Try to see it carefully. GPS signal we are receiving with a 2 megahertz bandwidth, and there are 10 satellites. So, each satellite the required satellite is giving minus 141 dBW power at the receiver, and there are 9 other satellite. Now, the for simplicity, okay, visible to the receiver, and for simplicity assuming power from each satellite receiver is minus 160 dBW. Okay. So, this is the noise power what you are receiving minus 141 dBW, and individual power from individual satellites are minus 160 dBW. So, 9 of them are coming individual and 1 required, each of them minus 160 dBW, and the required receiver has a noise power of minus 141 dBW. So, what is the signal to noise ratio? So, there are 2 types of noise happening here. One is it is getting its signal, that is minus 160 dBW, and 9 times of this signal, because 9 other satellites are sending this signal. So, that is interference, because GPS signal is overlapping each other, and also that particular receiver has a noise which is minus 140. So, noise and interference both informations are given. So, let us see, and this is minus 19 plus 19 plus minus 15 plus 15 dB, 4 options are given. Noise power associated with the signal over 2 megahertz bandwidth is minus 141 dBW. There are 10 satellites, each of the satellite is radiating. Receiver receives minus 160 dBW power from each of them. To receive a signal from a particular satellite, rest 9 satellites will create interference to the signal. It is a GPS CDMA type of signal. So, interference signal strength is minus 160 and 9 times. So, plus 10 log 9, which is minus 150.5 dBW, that is interference. So, the noise and interference, that is total noise power including interference, is the noise power is already given minus 141, and this interference we have found out, convert into ratio, add the powers, and you get a value like this, which if you convert to dB it becomes minus 140.7 dBW. So, this is total noise plus interference to a particular receiver, and the signal the receiver is receiving, each of them is minus 160 dBW. So, signal to noise ratio can be calculated as minus 160 plus minus to minus 140, that becomes plus. So, plus 140.7, it becomes minus 19.3. But when you do this calculation, there may be some calculator, I mean up to how much decimal places you are taking. So, it may come out to be 140.5 or 140.54, some numbers will appear depending on. So, we are getting minus 19 more than minus 19. So, the nearest value will get minus 19, and which is closest option is A. So, let us go to another one. This is more elaborate. Let us read the question. A multiple carrier satellite transponder operating at 6 gigahertz uplink and 4 gigahertz downlink has transponder saturation flux density of minus 67.5 dBW per square meter, and corresponding saturated EIRP is 26.6 dBW. So, at this flux density minus 67.5, if it is coming to the input of the satellite, the output EIRP, which will be saturated EIRP, 26.6 dBW. Since there are multiple carriers, the transponder has to operate in the linear region. In the saturated region, it will be creating nonlinearity and related problem. So, in the linear region, if we have to operate, we back off the operating point from the saturation by 12 dB for the input. So, there is a 12 dB input back off, and the satellite power amplifier characteristics specify that for every dB of input back off, the output back off changes by 0.5 dB. If the satellite G by T is minus 11.6 dB per Kelvin, satellite to earth station range is 40,800 kilometer, and the earth station G by T is 40.7 dB per Kelvin, find the total C by N naught. So, there are frequencies for the uplink and downlink given, the saturation flux density at the input of the satellite given, and corresponding EIRP saturation is available. The operating point is given in terms of input, and input to output ratio relation is also given. For every dB change in input back off, output back off changes by 0.5 dB, relation is given. Satellite G by T is known, range is known, and earth station G by T is known. So, you have to calculate the uplink C by N naught, downlink C by N naught, and find out the total C by N naught. Let us see. So, first let us recollect this concept, that the nonlinearity of the satellite amplifier goes like this. So, the saturation point in terms of input power to output power, if we draw, then at the saturation point we call it input saturation, that is P I saturation. Sat is not satellite, it is saturation, and so corresponding P out saturation we get a point, but this is nonlinear region. So, we have to give a back off at the input. So, depending on the characteristics of the satellite, there will be a output also will come down from saturation. So, if you can find out this operating point, we know what is the EIRP, actual EIRP from the satellite. So, the downlink side will come out clearly, but it is not given in terms of power input and power output, it is given in terms of input flux density, power flux density to EIRP, and we know that relation, that input power is proportional to input flux density. Obviously, input power is proportional to input flux density, and output power is proportional to the effective isotropic radiated power. These are obvious reasons, you know that. So, in the same characteristics can be put in terms of psi and EIRP, that is this axis I can put it psi I, that is flux density input. So, there is a input saturation, that is saturation power flux density, psi saturation. So, corresponding EIRP axis I get a EIRP saturation, same thing. So, once this concept is clear, then let us look at the numbers. Saturation flux density is given minus 67.5 dBW per meter square, and uplink frequency is given. So, we can find out the spreading factor S in dB, that is 10 log lambda square by 4 pi. Now, lambda is known, our uplink frequency is known 6 gigahertz. So, corresponding value is minus 37.01 dB square meter or meter square, whatever way you say. Then in terms of back off, input back off for the operating point is given 12 dB, and the relation between input back off to output back off is for every dB 0.5 dB. So, output back off total will be for this input 12 dB, output back off will be 6 dB. So, now we know the output back off. So, uplink C by N naught is saturation flux density minus input backoff, that is the input flux it is reaching the satellite, then the spreading loss or spreading factor and G by T of the satellite minus K. So, you put psi saturation is known, we put this value, backoff is known, S value we have calculated, G by T of the satellite is given, K value is given. So, you get 100.5 dB hertz, that is uplink C by N naught. In the downlink C by N naught, before that we need downlink C by N naught path loss. So, path loss will depend on frequency and range, downlink frequency and range is already given. So, you calculate, it comes out to be 196.69 dB. Now, for the downlink C by N naught downlink is the EIRP, this EIRP is not is the saturation EIRP and the corresponding output backoff we know. So, this is EIRP minus output backoff is the operating EIRP plus G by T of the satellite minus downlink loss minus K. So, you put this value, EIRP is known, output backoff is known, G by T satellite, G by T, this is, I am sorry, this is a mistake here, this G by T will be the earth station G by T, G by T, this will be the earth station G by T, which is given as 40.7, this one has to be corrected. So, which is 40.7 minus 196.69 plus 228.6. So, you get 93.21 dB hertz. Now, we have already uplink C by N naught calculated in dB hertz and downlink C by N naught calculated in dB hertz. So, we go to that standard relation, total C by N naught is inverse is equal to uplink C by N naught inverse and all these things, these will be C by N naughts. So, you put the value, you get the total C by N naught is 92.46 dB hertz and our option was 92.5 dB hertz. Now, there is one small mistake I find, this is inverse written here. So, there is a mistake, okay. This has to be converted and this inverse has to be removed. Earlier one of the sum is also like that. So, here you get the ratio number and then invert this and take log, you get this value, this minus 1 is mistake. Okay. So, appropriate of choice is B. Receiver antenna observes rain attenuation of 7 dB. The receiver noise figure is 2 dB and the receiver antenna gain is 40 dBi. Using power control fade mitigation technique FMT, how much increase in downlink power is required? Assume negligible clear sky noise temperature and temperature for the rain is 275 K and temperature for the receiver is 290 K. This temperature is physical temperature. So, what is given is rain attenuation is given and the noise figure of the receiver is given. Receive antenna gain is given and how much increase in the downlink power is given because the rain is attenuating, let us see. So, there are 4 options given A, B, C, D, different numbers, let us see which are nearest number we get. This is the scenario, a satellite, rain in between and the earth station. The rain attenuation is 7 dB, convert into number it becomes 5. Sky noise is negligible, so it is 0 and rain temperature is given as 275 K, physical temperature of the rain. So, antenna noise temperature during the rain is physical temperature of the rain and the loss due to rain minus 1 my loss, this is in numbers not in dB. So, if you put that you get the antenna noise temperature during rain is 220 K and the received noise figure was given as 2 dB which is ratio 1.58. Sky noise is negligible, receiver noise temperature without rain, when the rain is not there, sky noise temperature is negligible. So, it is physical temperature of the receiver and noise figure minus 1, this is in ratio it should be. So, that is 1.58 taken. So, 290 into 1.58 minus 1 which comes out to be 22.25 dBk. This is without rain receiver noise temperature. So, the system noise temperature during rain is, this is the input noise, the antenna noise temperature during rain and this is the receiver noise temperature. add them together you get 25.9 dBK. So, this is system noise temperature during rain. So, what will be the G by T during rain? That is G is already given 40 and this value is 25.9, you subtract. So, G by T during rain is 14.1 dB per Kelvin. This is during rain, and let us find out that when rain is not there, then without rain is already we have receiver noise temperature 22.25. So, subtract that from 40, that is G by T. So, it becomes 17.75 dB per K. So, the reduction in G by T due to rain is 17.75 when rain is not there, and when rain is there it is 14.1. So, reduction is 3.65. So, now G by T is reduced and the rain has already introduced some attenuation. So, two types of losses we are getting in the C by N. To maintain the C by N, let us see, during rain C by N will be reduced by the attenuation due to rain and the G by T reduction due to rain, that is delta G by T amount. C by N in clear sky is EIRP G by T by G by T at clear sky, path loss, etc. This is free space loss, same as path loss. During rain there are two things are happening, G by T changes during rain and attenuation during rain is coming. These are all in dB. So, these two terms, this term has changed from clear sky to rain, that is G by T, and a new attenuation is coming as a rain. So, that is during rain. So, the change in the C by N naught due to rain is, you subtract these two and you get delta G by T and A rain. These two factors are changing. Now, so if I want to make the C by N rain, I know, and in that if I add this factor I get a clear sky, that is what C by N naught rain plus this delta C by N. If I do, then C by N naught rain plus delta G by T plus A rain, which is delta C by N, that becomes C by N naught clear sky, and C by N naught clear sky is what? EIRP. Now, C by N naught rain plus this. So, EIRP plus delta G by T plus A rain, and G by T during rain minus A rain minus L free space minus K is all there, and you get C by N naught clear sky. So, to get back to the same C by N, due to rain your G by T and A rain has come, but this amount if I increase in the EIRP, then I get back the same clear sky. So, increase in EIRP is delta G by T plus A rain. Delta G by T is 3.65, A rain is 7. So, you add them together you get 10.65 dB. The correct answer is C. You have to understand this thing, that is two factors are coming, one is G by T is reduced, another is the rain is attenuating the signal. So, both the factors have to be considered, and for the fade mitigation to come back to the clear sky C by N naught, you have to increase by these two amounts together. Let us see the next one. Assume rain rate for two locations A and B which are situated on the same longitudes of a geostationary satellite. Station A same longitude, note the station A is 40 degree north and station B is 41 degree north, and both stations have same altitude. One is the same longitude and they are at the same altitude. For equal rain height at both the station, imaginary this much far away okay, let's during the monsoon it is happening, let us say the rain attenuation from the stations to satellite link, station A and station B, station to the satellite link, the attenuation from A and attenuation of B, either A is greater than B, are they equal, or A is less than B, or it cannot be determined with these numbers. So, let us look in these type of cases, you draw the picture. So, if you draw the picture, how does it look like? Mean sea level, our stations will be at the mean sea level, and there is a rain height. Assume that is a stratiform rain at both the stations, same amount of rain is happening, height remains same, and this is the melting level. So, this is height. Now, I have a station A which is 40 degree north, and it is the longitude, and towards the equator the satellite is at on equator GEO satellite. So, it will have certain elevation angle and it is reaching towards GEO, and there is a station B on the same longitude, but it is at 41 degree north, 1 degree away in the north. So, it will look at the geostationary satellite, same mean sea level, the height of the stations are also same from the mean sea level. So, A station will have a elevation angle to the geosatellite which is theta A, and station B will have a elevation angle theta B, and you can see since they are away, B is away from A towards the north, this theta A and theta B are not same, and there is a path loss in the A signal which is going to A or coming to A. There is a path loss which is attenuation, rain attenuation loss, which is L A, rain attenuation, rain path, it has attenuation loss, and at B, station B, it has a different rain attenuation loss. Now, we have theta B is lower than A because it is at higher longitude, northern side, you can see itself because GEO is remains same. So, this elevation angle theta A is larger than theta B, or theta B is smaller than theta A. So, obviously, the length of the path through the signal through the rain L B is more than L A. By simple this logic, you can say that the signal will be attenuated more here. So, appropriate choice is C. Let us look at the last question. At the end of life, LNA gain of an station is expected to decrease by 3 dB from the beginning of its operation, but the antenna gain and the antenna noise temperature remain same. Then G by T of the station at end of life will remain same. Will it increase from the beginning of life, or it will decrease, or none of this? Let us see the logic. We have seen that if we cascade two amplifiers with different gains G1 and G2 and their own effective noise temperature T1 and T2, the cascaded value will be the total system temperature will be the T1, the first stage, plus T2 by the gain of the first stage. Now, if this Ts at beginning of life, so gain at the beginning of life, this is, let us assume G1 is our LNA gain. So, first stage is LNA, and similarly at the end of life, the system noise temperature Ts at EOL will be T1 plus T2 by G1 at end of life, and it is given that end of life the gain of LNA or G1 is 3 dB lower than G1 at the beginning of life. So, therefore, this term, second term, the G1 is coming in the denominator. Since G1 at EOL is less, so the second term, which is T2 by G1 at EOL will be more than T2 by G1 at BOL, beginning of life. So, this is the noise temperature of end of life, system noise temperature at the end of life will be more, system noise temperature at end of life will be more than system noise temperature at beginning of life, and it says that antenna gain and noise temperature, all these things remain same, all other factors remain same. So, G by T, that is antenna gain G by system noise temperature at end of life, since EOL is larger, G by T will be smaller than G by T from the beginning of life. That is the option C, that was the correct option. So, with this we close, but you check always the whatever I have shown here, the certain errors cropped up, that you should correct it yourself, because you know. And in case of during the last weeks the discussion, if there are some errors you might monitor, or you may see, that you can inform us, or whatever we have observed, that comes in the process of discussion, certain errors. Okay, thank you very much.